moving ahead. Again, respiratory system, simple as possible. It's awkwardly simplified anatomy and physiology. Here's our fourth little installment right here. Again, a review to back up the good materials you have in your general practice questions, the power quizzes, the textbook, the PowerPoints, the guided reading. Oh my gosh, all those other things that are available to you. Okay, now what we're going to do is talk a little bit about the loading and unloading of the oxygen and how the conditions, the environmental conditions in the lungs and the cell are uniquely different to allow the loading to occur near the lungs and the unloading to happen next to the hard-working cells. So here we are in our generalized story. Okay, on this side right here we have a hard-working cell. Now next to a hard-working cell, here are 5 conditions that you would expect to run into. You would expect that next to a hard-working cell, there would be a higher temperature in this zone because this cell is creating ATP by burning fuels inside the mitochondria, and there's always waste heat in that process right there. So the hottest part of your body are the hard-working cells. So the temperature next to hard-working cells should be high. This is a place where oxygen should be unloaded, where you need to deliver the oxygen to these hard-working cells. Well, next to these hard-working cells, that's where the carbon dioxide level is going to be high. The temperature is going to be high, and the carbon dioxide level is going to be high because the cells are burning, say, glucose in the presence of oxygen to create water, carbon dioxide, capture some energy in the form of ATP, and they lose heat. Well, carbon dioxide is one of those products. It's a hard-working cell. So, therefore, you expect next to a hard-working cell there'd be a higher temperature and a high concentration of carbon dioxide. Well, the carbon dioxide can combine with water, make carbonic acid, which can then dissociate and release H plus ions. So you expect H plus ions to be increased next to hard-working cells. And wherever you have H plus ions, you have acid environment. And the way that we represent an acid environment is with a pH. So you've got a low pH next to these hard-working cells. So here we go. Let's sort of rearrange these things, make it a little easier to see. Next to the hard-working cells, you would have a low pH, low oxygen level, high temperature, high carbon dioxide, and high hydrogen ion concentration. These are all the conditions that assist oxyhemoglobin dissociating, that is, the oxygen being unloaded where it is needed. By the way, you'll also notice that when it comes to systemic precapillary sphincters, the conditions that cause systemic precapillary sphincters to open were low oxygen, high carbon dioxide, and a low pH. So those things specifically caused or allowed the systemic precapillary sphincters to open, to allow the oxygenated blood to get to the hard-working cells. So not only do these conditions allow the blood to get to where it's needed, but they also allow the oxyhemoglobin to unload more readily there. The opposite's found over here. Okay, over here next to the lungs, next to the relatively fresh air of the lungs in a well-ventilated part of the lungs, the temperature should be lower because the temperature of the atmosphere is probably lower than temperature next to your hard-working cells. Over here, it'll be richer in oxygen because the atmospheric air has more oxygen than this region over here. There'll be less carbon dioxide next to where there is fresh air inside the lungs. Because there's less carbon dioxide, there'll be less hydrogen ions, and the pH will be higher. So the conditions over here that are favorable when it comes to loading oxygen in the open air spaces of the lungs where the blood should go because there's good shopping, you have over here high pH, high oxygen, low temperature, low carbon dioxide, and low hydrogen ion concentration. So these are the conditions that make it easier for oxyhemoglobin to form, for oxygen to load. You'll also remember that when it comes to pulmonary precapillary sphincters, high oxygen, low carbon dioxide, and a high pH were conditions that assisted pulmonary precapillary sphincters to open, to allow the blood to go to that spot inside the lungs where the fresh air was located. So over here, it's all about shopping. Send the blood where the shopping is good. Over here, it's all about delivering. Send the product where it is needed. Now, these ideas right here, in all their cleverness, can get really, really complicated. And so here is a gross oversimplification of a very complicated idea. It has to do with the oxyhemoglobin or oxygen hemoglobin saturation curve. Now, in its simplest form right here, grossly oversimplified form, what we have is a graph in which we compare the saturation of the hemoglobin with oxygen to the partial pressure of the oxygen, which in essence represents the availability, the concentration of the oxygen. Now, a normal curve right here is represented in the middle, and that is when there is no oxygen, there's no saturation. Gee, that makes sense, 0 and 0. But as you make the oxygen available, it's more likely for the hemoglobin to pick it up. And so the saturation of the hemoglobin goes up as the availability of the oxygen goes up. You'd expect this to be a kind of a straight line, but it doesn't work that way. It turns out that it's easy to load the oxygen at the very, very beginning, but later on it becomes a little less dramatic. So you can still load the oxygen, but it's just not as easy. So the curve tends to go up dramatically, and then it kind of plateaus a little bit, flattens a little bit. So this is a so-called normal oxygen hemoglobin saturation curve. It goes up dramatically and then kind of plateaus out. Now, we can talk about situations where it is easier to load the oxygen and where it's easier for the oxygen to fall off. And so these things right here are called shifts. We can talk about a left shift and we can talk about a right shift. Left shift means it's more vertical and it's easier to saturate the oxyhemoglobin. Right shift means that the slope is not as dramatic, and now it is easier to drop off the oxygen from the oxyhemoglobin. So this is favoring oxyhemoglobin formation, oxygen loading. This is favoring oxyhemoglobin dissociation, oxygen unloading. Well, it turns out that two conditions that tend to favor the loading right here are an increase in the pH and a decrease in the temperature. So therefore, as we saw before down here, where the conditions are a bit cooler and a little more alkaline, it's easier to put the oxygen onto the hemoglobin. But over here, where the temperature is a bit higher and the conditions are a bit more acidic, it's not as easy to hang on to the oxygen. So these two conditions right here favor oxygen loading, as represented over here in the well-ventilated parts of the lung, and these two conditions represent or favor oxygen unloading, as seen over here next to the hard-working cells. And the oxygen hemoglobin saturation curve is just a way of visualizing that. So again, remember, a left shift is supposed to I hope I said that right. A left shift represents loading, making it easier to load, and a right shift represents easier to unload. This is what you expect next to the well-oxygenated parts of your lungs, the well-ventilated parts of your lungs. This is what you expect next to the hard-working tissues inside the cell. Once again, for folks who are thinking about respiratory therapy, oh my gosh, this is actually so much more complicated than this, but this is the simple story that we're looking at here now at the moment.